The universe may look calm from afar, stars shining, planets spinning, endless beauty. But behind that calm lies something far more mysterious, strange signals, unseen forces, and cosmic secrets that challenge everything we know. Tonight, we explore the iceberg of cosmic horrors, and what we find may change the way you see the universe forever. Level 1. The surface. Observable oddities. The WOW signal. In the summer of 1977, astronomers at Ohio State University's Big Ear Radio Telescope were conducting routine observations of the sky when they detected something truly extraordinary. For 72 seconds, a narrowband radio signal from deep space came through with an intensity and structure that was unlike anything previously recorded. It was so remarkable that one of the astronomers, Jerry Eman, who was reviewing the data, couldn't contain his excitement. He scrawled the word "wow" in red ink next to the signal on the printout. That single word became synonymous with one of the most enduring mysteries of modern astronomy. The signal, known as the WOW signal, was detected at a frequency of 1420 MHz, which is the natural frequency of hydrogen, the most abundant element in the universe. The coincidence of this frequency with the most fundamental building block of matter raised immediate questions. Could this be a message from an extraterrestrial civilization trying to reach out to us? The signal appeared to come from the constellation Sagittarius, close to a star system called Tau Sagittarii, which added another layer of intrigue. Its source seemed to be a distant location in the sky, well beyond our solar system. Despite numerous follow-up observations and efforts to detect a repeat of the signal, it has never been detected again. The search for its origin has spanned decades, and yet no definitive answer has been found. Some scientists believe the signal may have been caused by a natural phenomenon, such as a reflection of radio waves from space debris, or even a satellite passing overhead. Others remain convinced that the signal was something far more profound, possibly an intentional message from another civilization. The fact that the WOW signal has never been repeated only adds to its allure. It remains a tantalizing mystery, raising the possibility that we may have heard a fleeting whisper from an alien intelligence, one that may have been lost forever in the vastness of space. While many of the most advanced telescopes and equipment have failed to uncover any answers, the signal still stands as a beacon, a reminder of how much we have yet to learn about the universe. The Great Silence. Astronomers have been listening for decades, radio dishes scanning the sky, algorithms combing through petabytes of data, and yet no confirmed signal has ever said, unmistakably, "We are here." This unsettling quiet is known as the Great Silence. It sits at the crossroads of the Drake equation and the Fermi paradox, forcing us to ask why a galaxy with hundreds of billions of stars, many with Earth-like worlds, sounds so mute. Explanations range from the sober to the chilling. Civilizations may be rare or short-lived. Technological societies burn bright and vanish before their signals cross interstellar gulfs. They may speak in ways we're not listening for. Laser bursts, narrow beams, alien compression. While our search focuses on familiar radio bands, there's the timing problem. Our radio bubble is just about a century old. A faint whisper that fades with distance, easily swallowed by cosmic noise. Some suggest the zoo hypothesis, advanced beings watching, never intervening, or the Great Filter, a brutal bottleneck that few survive. Others warn of the dark forest, a universe where discretion means survival, and broadcasting is reckless. SETI and Breakthrough. Listen have expanded the search and refined our sensitivity, yet the result remains the same. No verified techno-signature. Perhaps the silence is not absence, but misalignment. Wrong frequencies, wrong epochs, wrong expectations. And so, we keep listening, not because we're certain an answer will come, but because this quiet, vast, ancient, and eloquent is the most haunting mystery we've ever heard. Tabby's Star. Tabby's Star, also known as KIC 8462852, is one of the most enigmatic and puzzling stars ever discovered in our galaxy. Located about 1,170 light-years away in the constellation Cygnus, it has been the subject of intense debate and curiosity since its discovery by astronomers in 2009 using NASA's Kepler Space Telescope. The star exhibits unusual and erratic dimming patterns that have defied conventional explanations. Unlike any other star observed, the dimming of Tabby's star is not gradual, but rather sporadic and sudden, with its light fading by as much as 20% over short periods of time. At first, astronomers thought this behavior might be explained by an uneven cloud of interstellar dust passing in front of the star. Dust clouds are a common cause of dimming in stars, as they block some of the starlight. Some researchers have gone as far as to speculate that the dimming of Tabby's star could be the result of an enormous structure orbiting the star, possibly built by an advanced extraterrestrial civilization. Tabby's star has become a symbol of the unknown, representing the limits of our understanding of the cosmos. Its mysterious behavior challenges the very notion that we can fully comprehend the workings of the universe, reminding us that there are still vast and uncharted territories beyond the reach of even our most advanced technologies. The Pioneer Plaque. In the late 20th century, humanity took a bold step toward communication with potential extraterrestrial civilizations. The Pioneer Plaque, attached to the Pioneer 10 and 11 spacecrafts, was designed as a universal message and invitation from Earth to any advanced intelligence that might one day encounter these spacecrafts as they drift into the cosmos. These spacecrafts, launched by NASA in the early 1970s, were the first human-made objects to travel beyond our solar system. And with them, they carried a message of who we are, where we come from, and our hope for peaceful communication with other civilizations in the galaxy. The plaque is a simple yet profound symbol of human ingenuity. Made of anodized aluminum, it is designed to withstand the harsh conditions of space for billions of years. Etched into the surface are a series of carefully chosen symbols and images meant to convey basic information about humanity and the planet Earth. These include a figure of a man and a woman, a map of our solar system, and an image of the spacecraft itself. The purpose of these images is to provide a way for any extraterrestrial being that might encounter the plaque to understand who we are, even if they come from a completely different planet, culture, or technological background. However, the plaque also raises deeper questions about our place in the universe. If these spacecraft were to be found, if an extraterrestrial civilization were to decode this message, what would it mean for humanity? Could we make meaningful contact with beings from another star system? Or would they view us as primitive, fragile creatures? And if they responded, how would we handle such a profound communication? The Pioneer Plaque embodies both hope and vulnerability, a small and fragile message sent into the vastness of space, hoping to bridge the unimaginable distances between stars. Level 2, Beneath the Surface, Unsettling Discoveries. Oumuamua, the first interstellar visitor, discovered in October 2017 by the Pan-STARRS survey, Oumuamua arrived on a steeply hyperbolic path, proof it came from beyond the solar system. It was tiny by asteroid standards, likely only tens to a few hundred meters across, yet its light curve swung wildly, implying an extreme shape and chaotic tumble. Early models favored a cigar. Later work suggested a thin, pancake-like body. Either way, nothing in our catalog looked quite like it. Then came the real puzzle. As it receded, it experienced a small but measurable non-gravitational acceleration, as if a gentle thrust were nudging it away from the sun. Comets do this via outgassing, but Oumuamua showed no visible coma or tail. Spitzer saw no obvious CO2 or THEO. Hypotheses multiplied, sublimation of hard-to-see ices like hydrogen or nitrogen, venting through tiny fractures, even ultraporous fractal dust pushed by sunlight. No single explanation has won. Oumuamua left us with a tantalizing absence, a first interstellar visitor that obeyed the data, but slipped past our categories and was gone before we could chase it. Dark matter and dark energy. Only about 5% of the universe is the ordinary stuff we can see and touch. Stars, planets, gas, and dust. The rest hides from our eyes. Dark matter shows up through gravity, not light. Spiral galaxies spin so fast at their edges that, without extra unseen mass, they should fly apart. Clusters of galaxies also need more mass to stay bound. Background galaxies appear stretched into arcs by a phenomenon called gravitational lensing, which again points to additional invisible mass. Even maps of the cosmic microwave background, the faint afterglow of the Big Bang, favor a universe filled with matter we cannot see directly. A dramatic case is the Bullet Cluster. After two galaxy clusters collided, the ordinary hot gas slowed down and glowed in X-rays, while most of the mass, measured by lensing, slipped ahead as if it barely interacted with anything except gravity. What is dark matter made of? Leading ideas include weakly interacting massive particles, often called WIMPs, axions, and sterile neutrinos. All would pass through normal matter, almost without a trace. Underground detectors and sky surveys keep improving, but they have not made a confirmed discovery yet. Some scientists explore another path, change gravity itself on large scales. This family of ideas, such as modified Newtonian dynamics, can match some galactic data, but struggles with the full set of cosmological tests. Dark energy is even stranger. It acts like a negative pressure that speeds up the expansion of the universe. In 1998, measurements of distant Type 1a supernovae showed that galaxies are receding faster than expected. Combine that with the cosmic microwave background and patterns called baryon acoustic oscillations, and a simple picture emerges: roughly 27% dark matter, about 68% dark energy, and about 5% ordinary matter. The standard model is called lambda CDM. In it, dark energy behaves like Einstein's cosmological constant. Physicists describe it with a parameter called W that is about -1. But why is the cosmological constant so tiny and yet not zero? Could dark energy change over time, like a slowly rolling field, sometimes called quintessence? Current debates, including the so-called Hubble tension between early and late measurements of the expansion rate, hint that we may be missing something deep. For now, dark matter builds the scaffolding of the cosmic web, and dark energy pushes the voids wider, two invisible forces shaping the universe we see. Black holes. A black hole is a region where gravity grows so strong that nothing can get out, not even light. Cross the event horizon, and every possible path points inward. Most stellar black holes are the ashes of giant stars that collapsed when their nuclear fuel ran out. At the centers of galaxies live supermassive black holes with masses of millions or billions of suns. We do not see black holes directly. We infer them from what they do to their neighborhoods. Gas spirals in to form a blazing accretion disk that heats to extreme temperatures. Powerful magnetic fields can launch twin jets that shoot out at nearly light speed and light up intergalactic space. Einstein's theory predicts that time slows near a black hole. To a distant observer, a falling clock appears to tick slower, and light from the clock shifts to redder colors. Cross the tidal zone, and the gravity difference between head and feet can become severe. Astronauts call this spaghettification. In 2019, the Event Horizon Telescope released the first image of a black hole shadow in the galaxy M87. In 2022, it revealed the shadow of the one in our own Milky Way. In 2015, the LIGO detectors heard the first gravitational waves from two merging black holes, a ripple in space-time itself. Open questions remain. Hawking radiation hints that black holes can slowly evaporate over unimaginable times. Yet, what happens to information is still debated. Do all black holes have simple final states, or can subtle quantum details survive near the horizon? We keep pushing for sharper images and better detectors, because these dark engines are laboratories for gravity at its most extreme. Cosmic microwave background anomalies. Imagine a faint glow that fills the entire sky, the last light left from the Big Bang. It's called the cosmic microwave background, or CMB. It's the oldest light in the universe, nearly 14 billion years old. When satellites like WMAP and Planck mapped this radiation in detail, they discovered that it isn't perfectly smooth. There are tiny variations, small warm and cool spots, and they match almost exactly what our cosmological theories predict. Almost. Because among all that predictable noise, a few things stand out. Things no one has fully explained. First, the largest waves in the universe are strangely quiet. It's as if someone turned down the volume on the universe's lowest notes. Second, two of the biggest temperature patterns appear mysteriously aligned, and, what's even stranger, they line up almost perfectly with the plane of Earth's orbit. Scientists jokingly called it the axis of evil. because coincidences like that shouldn't exist in a random cosmos. There's also a north-south asymmetry. One half of the sky looks a little rougher, the other smoother. And then there's the cold spot, a huge eerie blue patch on the CMB map. It was first noticed by WMAP and later confirmed by Planck. Some say it's just a statistical fluke. Others think it might be caused by a gigantic supervoid, an empty region of space that drains energy from the light passing through it. Scientists have also found smaller oddities, like gravitational lensing that seems slightly stronger than expected. None of this breaks the standard model of cosmology, but it does hint that the early universe might be hiding unknown physics, or that we still don't fully understand the tiny imperfections in our own measurements. Either way, the oldest light in the universe still keeps its most haunting secrets, in the quiet places where the cosmos itself seems to fall silent. Multiverse theory. The multiverse is not a single idea, but a family of hypotheses that suggest our universe may be one island in a vast archipelago of realities. In inflationary cosmology, rapid expansion in the first instant after the Big Bang could have created many bubble universes. Each bubble would stop inflating at a different time, freeze different quantum jitters into matter, and perhaps settle on different values for the constants of nature. In quantum mechanics, the many worlds view says that every quantum event does not pick one outcome. Instead, the wave function includes all outcomes in parallel branches. String theory adds another path. Its equations allow many possible vacuum states, often called the landscape, each corresponding to a universe with its own particle masses and forces. There are also proposals that black holes might spawn baby universes on the inside, with new spacetime budding off beyond the event horizon. Can we test any of this? Perhaps. A collision between our bubble and another could leave a circular scar in the cosmic microwave background. Variations in the constants of nature across the sky could hint at neighboring domains. A background of very ancient gravitational waves might carry the fingerprint of inflation. So far, no clear sign has appeared. Critics warn that a theory which explains everything risks explaining nothing. Supporters counter that the multiverse helps address fine-tuning, the puzzle of why physics seems set to allow life. Wherever the truth lies, the multiverse forces a humbling thought. What we call the universe may be only our patch of a far larger reality. Level 3. The Abyss, the Unknowable. Time Travel. Paradoxes. Time travel sits at the edge of physics and philosophy. Einstein's theory allows curved paths in space-time, and some exact solutions hint at closed time-like curves. Rotating universes in the style of Gödel. Infinitely long, rotating cylinders, sometimes called Tipler cylinders, and hypothetical traversable wormholes all suggest that, in principle, a traveler could loop back to an earlier moment. That possibility collides with logic and famous paradoxes. The grandfather paradox asks what happens if you prevent your own ancestry. The bootstrap paradox asks where an object or a piece of information comes from, if its origin is a loop, like a manual passed to the past that writes itself. Physicists have proposed 3 main escape routes. First, the Novikov self-consistency principle says, events adjust to avoid contradictions. You can go back, but every attempt to change the past bends into a consistent outcome. Second, many worlds thinking says each intervention branches reality. So you do not rewrite your own past, you step into a sibling history. Third, Hawking's chronology protection idea suggests that quantum effects destroy time machines before paradoxes can form. So far, there is no experimental evidence for time travel, and every realistic attempt runs into impossible engineering, exotic matter, or instability. Yet the paradoxes remain valuable. They stress test our ideas about causality, free will, and the difference between what equations permit and what nature allows. Simulation hypothesis. The simulation hypothesis suggests that our reality could be an engineered environment running on some advanced substrate. The most famous framing comes from philosopher Nick Bostrom. He argues that at least one of the following must be true. First, almost no civilizations reach a technological level capable of running ancestor simulations. Second, such civilizations choose not to run them. Or third, simulations vastly outnumber base realities, which makes it likely that we are inside one. None of these options feels comfortable. Either intelligence tends to destroy itself, or it survives but refuses to look back, or we are already looking out from inside a designed world. Why do people take this seriously, and not just as science fiction? One reason is computing power. Each decade, our ability to model worlds grows. We simulate weather, oceans, entire galaxies, and virtual societies of agents that learn and compete. Scale that up by thousands or millions of years, and the idea of rich interactive histories becomes less absurd. Another reason is physics itself. The universe looks quantized, with the smallest meaningful unit of length and time, and rules that appear algorithmic. Quantum events are inherently probabilistic, as if outcomes are sampled rather than written in stone. Cosmic fine-tuning adds to the unease. The constants of nature sit in ranges that allow stars, chemistry, and life. A simulation could simply set those values, what would count as evidence. Some teams have proposed looking for a lattice signature in very high-energy cosmic rays, as if space had a hidden grid that slightly distorts particle paths. Others hunt for small violations of symmetries, timing glitches, or compression artifacts in astronomical data. So far, there is no clear hit. A designer could also hide the tracks well, render only what is observed, and obey strict rules like conservation laws and no faster than light signaling. In that case, every clever test becomes a mirror that reflects our own assumptions about how rendering should work. There are strong counters. The energy cost of simulating an entire universe with full fidelity might be astronomical. A more likely path is a selective simulation, focused on observers and their surroundings. That raises ethical questions about consciousness and suffering. If we are simulated, does our experience still matter? The practical answer is yes. Pain feels like pain. Love feels like love. Meaning is not erased by the medium that carries it. The hypothesis, then, is less a recipe for despair and more a prompt to humility. Either we inhabit a base reality and are responsible for the only world we know, or we are inside a crafted one and still responsible for what we do within it. In both cases, curiosity remains our best tool. We push on the edges of the rules, not to break the world, but to learn how deep it goes. White holes. In general relativity, a white hole is the time reverse of a black hole. If a black hole is a one-way entrance where even light cannot escape, once it crosses the event horizon, a white hole is the one-way exit. Nothing can fall in from the outside, yet matter and light could in principle come out. The idea is not fantasy. There is a perfectly valid solution to Einstein's equations that contains both a black hole and, on a separate region of the same mathematical spacetime, a white hole. Join the two, and you get the old Einstein-Rosen bridge, the ancestor of what we now call a wormhole. On paper, it all hangs together. In nature, the story grows messy. First, stability is a problem. Real space is never perfectly quiet. A single grain of dust, a whisper of radiation. Any small disturbance aimed at a white hole horizon tends to blow up the solution and make the horizon collapse. In practice, that means a white hole would be violently unstable. Second, the arrow of time matters. The time-reversed flow that a white hole represents looks like entropy running backward. Accretion disks around black holes turn ordered falling gas into heat and radiation. A white hole would have to take heat and random photons and conjure ordered jets of matter. Physics does not absolutely forbid rare decreases of entropy, but the odds are so tiny that the universe would never notice. What would convince us? A perfect white hole would show an outward-only horizon, and a burst whose spectrum and timing did not match any known engine like a magnetar, a merger, or a jet from a black hole. We would also need a theory that predicts rates and energies that match the sky. Today we have neither a clean prediction nor a clean detection, and yet white holes serve a purpose. They are a mirror held up to our ideas about time, causality, and quantum gravity. Even if nature never builds one, chasing them sharpens the questions we ask black holes and reminds us that every solution on paper must survive the noise of the real universe. Wormholes. A wormhole is a hypothetical shortcut through space-time, a tunnel that links two distant regions so that a traveler could leave one mouth and emerge almost instantly from the other far away. General relativity does allow such structures in the mathematics. The earliest version is the Einstein-Rosen bridge, which connects a black hole to a mirror region, but that bridge pinches off too quickly to cross. In the late 1980s, physicists Kip Thorne and Michael Morris described traversable wormholes that, on paper, could be held open long enough for a person or a probe to pass through. There was a catch. To keep the throat from collapsing, the tunnel would need so-called exotic matter, material with an average negative energy density that pushes rather than pulls. Classical matter does not behave that way, and most energy conditions and relativity forbid it. Quantum physics, however, allows small pockets of negative energy in special setups, like the Casimir effect between closely spaced plates. If traversable wormholes exist in nature or can be engineered, they could cheat distance without breaking the speed limit locally. A ship would always move slower than light in its own neighborhood, yet cross light years in a heartbeat by taking the shortcut. For now, wormholes are best treated as thought experiments that probe the edges of physics. They force us to ask where gravity meets quantum rules, and whether nature permits shortcuts that do not tear logic apart. Cosmic horror. Cosmic horror is not about monsters in the corner. It is about the moment you realize the universe does not notice you at all. Space is vast beyond feeling. The Milky Way alone holds hundreds of billions of stars, and there are hundreds of billions of other galaxies. On these scales, our lives look like sparks. This is not fiction. It is the sober view from astronomy and physics. The laws that shape galaxies and black holes do not bend for us. They will keep working long after the last human word fades. Start with time. The universe is about 14 billion years old. Stars are born and die in nuclear fire. In the very far future, star formation will slow, fuel will run out, and most matter will fall into black holes. If dark energy keeps pushing space apart, every island of matter will drift away from every other, until nothing new can cross the gaps. Some models end with heat death, where energy is spread so thin that no work can be done. Others allow a rare and sudden vacuum decay, a bubble of lower energy that would erase everything at light speed, with no warning and no pain. Both endings are indifferent. They do not punish. They do not forgive. They simply happen. Even in the near universe, there are sharp edges. Gamma-ray bursts can sterilize worlds across light years. Supernovae seed life with heavy elements, but also scorch it. A black hole's event horizon is a perfect silence. Cross it, and no message returns. The cosmic microwave background is a baby picture of everything, but it also reminds us that we live inside rules we did not choose. The great silence in the search for life may be the loudest note of all. Either minds are rare, or they do not last, or they do not speak in ways we can hear. None of those options is gentle, and yet this view is not a command to despair. Cosmic horror clears away comforting myths and leaves something strict and bright. Meaning does not arrive from outside. We write it here, in the only place we know. We build instruments that catch a handful of ancient photons and turn them into maps of the first light. We listen for whispers on the hydrogen line. We time the tremor of space-time after black holes collide. In a universe that does not promise safety, curiosity becomes courage. Wonder becomes work. The scale that makes us feel small also gives us a canvas without borders. To face that, and still make something true and kind, may be the bravest story we can tell. As we peer into the cosmic abyss, we are confronted with more questions than answers. The universe, in all its grandeur and mystery, continues to elude our understanding. Perhaps in the vast expanse of space, we are not meant to know everything. But in our quest for knowledge, we find the true horror, the realization that the more we learn, the less we comprehend.